Okay, we're starting the streaming. So this is the episode 3 of building an emulator using Rust. Uh, Today we will be continue reading the ROM file. Actually, starting no, we started it yesterday, and we will be decoding the opcodes as soon we are reading, and as soon we get something to show on the screen, we will be doing those stuff. I already read that this I already got some documentation and then build this draw of memory. Also, we have this CPU representation here because we have those 8 registers plus program counter and the stack pointer. This 2 is 60-bit. All those are 8 bits, but they can be used together to be 16-bit. Also, there are two things that I still need to figure out how to handle. But as I said, I will try to going, and then as soon as I get there, I will be worried with that. But one of those is the clock speed, because there are this part of the instructions that they say, okay, for example, this 31. So this instruction it has 3 bytes, and it consumes 12 clocks. It's here. The clock 12 cycles. That's the cycle of the Game Boy CPU. I'm not really sure how to simulate that in the code yet, but I will not worry about that now, because I think that when we get there, the side effect of this will be some weird stuff happening in the screen, and so let's first get to coding the LCD part, the display part, and then we start worrying about that. As I said yesterday, the LCD will be also very challenging, because we need to understand better how these ROMs will work and how to manipulate it. But let's see how that works. Oh yeah, there is other stuff that is so I said 2 stuffs, right? 2 things that I need to figure out how to understand it better. So one is the clock, the cycles, the number of cycles, and the other, actually 3. The other is, but that one of those are just in the code. I need to figure out how to decode this and get the right size from the memory, because sometimes it's just 2 bytes, 3 bytes, or even 4 bytes, depending on the arguments of that function. And the other part, which is hard, it's handling the interruptions, which will make, I think it's totally related with the display and sound. let's see. Let's see what we get here. We'll do some code today and see if we can get some progress. Then it will be okay. So let's go. So now we are reading, as I said yesterday, we are reading this boot room, which is just a small part. It's not a entire ROM. It's just this very small part, which will be overriding anyway this first 255 bytes when an actual ROM get there. It's used by Gameboy to perform some checksums in initialization. So let's read this. Let's create a structure to read this, to load this in the memory and so on. Maybe I can even today change this instead of run boot ROM, run the normal ROM and see what's going next. Okay, so let's do. Yesterday we get this. So if you see, we are just reading the file, this file, which is a binary file, and let me put it bigger. Okay, so actually this last part here is this. So this part here is this, because this is the end of the file, right? We are just reading from so let's continue. Okay, first things first, I want to have this in place, this CPU representation in place, because we have the registers, we have this which is used to execute any instruction, and we also have this program counter. So this is the basic stuff that we need to have in our structure. So I have created here, I'm still working in one single file here in Rust, then later I will refactor, create, but let's keep us things simple for now. Actually, anyway, it's simple anyway. So this, okay, so first of all, the memory, let's name it run, the entire run. So this is the entire run, and it's not 32 kilobytes, but actually it is 60. So it's 64 kilobytes. So it is So it is 64 kilobytes. Okay, actually 60. here, otherwise it will be overflow. Okay, so it's no, actually it's 6 because it's go from 00 to FFF. Okay, great. This CPU is, so we need to have these registers here. So let's create it. You wait. All of them are binary bytes. So wait. You wait. F you wait. H you wait. Those two could be put together also, but let's handle that later. My hands are cold. And okay, PC and yes. Okay, great. So first things first. So let's implement something here. It is okay. Implement what I want to do here. So create a new memory, which should be memory. Initialize it with zeros. Okay. Yeah. Sorry. Actually, I'm great. Yeah. Which will return a memory. Of course, this is the constructor. New is a convention for a constructor in Rust. It's kind of constructor because this is not a real class. Well, it's a struct. And return it. So yeah, we have a new memory here, a new memory object, all initialized with zeros. A big array. I need a way to write. So then write byte. Yeah, because we will be writing byte a byte. So this is the way that we create an instance method. So a method, not a static one. This is static one. This is a method. the instance of the instance. So this will be, since it is an array of 16 for 16, so these will be the keys, right? The first key, this is the memory address, this is the memory address, so it's the first key of this array, of this vector, no, this array. And this is the, so it's a 16-bit addresses, because our program counter is 60-bit address. So let's do this. Let's accept an address type of 16 and get the value, the real value to be a byte. And what it does, just address value. Complains about something. No field is main on type. Oh. It's run. And I use it here. Yeah, this naming. I could be use it main. New memory. Inside the memory we have RAM. This is weird. Anyway. Now what's the error? Slice inside indices are typo. Slice indices are typo. Oh. This? Yeah. Okay, so we have a function to write. Then I need a function to read a byte. Which of course will not. Just return this. Okay, so that's fine. Okay, we have this memory and CPU, but I think we can put something here, like the Game Boy, well, the machine, because then we can put those things together. Okay, Game Boy. So we have this pod structure, Game Boy. Wait, okay, so the CPU, okay, let's Let's implement structure for CPU. CPU. So we do hit the CPU, of course. Let this CPU be CPU, and everything on 0. So replace from this line. This is not a 0. This is innovate. Okay. So you have here 0, 0, 0, 0, 0, and hit turn the CPU. Okay. What is this? Why? Okay, let's see if it's still compiling. No, it's not compiling anymore. Why? Oh, yeah, sure. I did this. No, I think it will compile. Oh, so yeah. I need to learn more motion, so VI. Okay, so I think it's good. Still running. So we have this. So we can do like. So we have our own file. Yeah, we can do this. Can yeah. I think we can do this like let mem equals memory new, okay, and then mem write byte. Okay, actually can I convert a vector? Oh, I think so. Well, let's do this. It's better. Okay, so let mutable memory equals to memory new. Okay, and then here, instead of printing, will be writing. Okay, so how we're getting the address? Because here we need to have an address, which will be like 0, 0, 0, 0, and the byte, right? But they should increment on every when I do this. I think I can get the vector, because this is a vector. Convert vector. I lost. This is interesting. So I have this ROM file and I have my mutable array, which is main.run. Okay. So maybe I can do this like pub function from ROM file. It will receive the bytes. Oh, let's see, ROM file. As a reference of vector. And it will do not return anything, because it will, of course, it should receive mutable self. And I can do this. This part I did not understand. I get ROM file. Oh, I'm getting from the beginning. Oh, I'm getting a slice here. Yeah. No, a slice of self-run. Here's a range. I'm expanding the. I think I'm expanding this, so let me put it all here. Let's see. And self run dot copy from slice bytes. Into this. I think now if I do this man from ROM file, pass the ROM file. No. Yeah, it's a lot of manage first slice. Let's see. Yeah. So maybe do this. Got it there. Let me see. Okay, so I will do something very boring here. I do something simple, then later I will do this. This, right? Okay. Now I have this, I think. How can I get a counter? Rust eater. Back. Over slice. I think in the book there is a rust. Okay, so vectors. Okay. Maybe this. Let's do this. probably not this best way of doing this. Okay, it compile. So if I do now, let's do something like, let's see, I want to read okay, so now I want to read the okay, let's see, like a 0, 0, 0, let's see. So I need to get a byte. Actually 3, right? So no, let's do this. Let's implement this run function, run instruction. So I will run an instruction actually. The instruction itself, because I will modify the registers and I will receive it and this is interesting. Well, let me do this before, because I need to read. Okay, so let me do this first. If I do like this, okay, so man, so just do this, like byte on 0. Okay, oh, 0, 0, 1, 0, 0, 0. Okay, so then I do man bit byte 0, 0, 0. What happened with the music? No more music. Okay. So then, let's see. Nothing. Nothing. right here. Let me see. So I write. So write. So let's do this first. Print. Okay, so yeah, at least the others are doing good. Wait. Yeah, because if I have only 260 255, so it's only the, yeah, it's right. So I'm doing this. Can I do this? From self run. I think it will say that it's not. Okay, I will derive. It's what's that? How that is derived? Derive. So just use derive debug. Why is that? Don't implement. I need to implement this. Okay, so if now, well, then I can do this, right? I think so. Why not? Why? Oh, as use sites? Yeah, now it's safe. Oh, that's the point. So I think I need to do this. Oh, so that's it. So put this. No. Oh. Expected what? I. Oh, it don't need to be. Oh, yeah. So two things here. One, I was not returning it, and I had a semicolon here. So yeah, this is Rust. Man, I'm not Rustician yet. Of course, otherwise I need to do a return. I was trusting this last line, but the last line should have no semicolon. That was the problem. So if I go now and I do this, yeah. So let's see. If I go to the byte 0, 0, 0, it is 49. Okay, but I want to read it as no. I want you here to do as U16. No. Yeah, I need to do this to be able to see that 31. Yeah, 31. So yeah, we put the code and we are able to see here. So let's put like a 010. See? Yeah, 11. Okay, so we are able to load a file into our memory array, and we are able to index it as an 60-bit address using 60-bit address. So we can, using 60-bit address, we can then. I don't need this anymore. Okay. Put the ROM file into the memory RAM. Okay. So now we can go buy it. Now it's something nice because now we have this PC, which is a 16, the program counter, which is a 16-bit. So then we can do something like this. We can do a loop. and do something like CPU run instruction, passing the program counter. Yeah, the reference to program counter. No, run instruction. Yeah, run instruction or run next instruction, because it will come. Okay, so run instructions. Make CPU run instructions over the RAM. Instructions. Okay, so the CPU should have memory. No. Yeah, it will receive the memory. Yeah, let's see that over RAM. So it will receive RAM, mutable. It will receive the, yeah, because it will mutate. Then we will create new. So let's CPU equals CPU new. So now we have this. We have CPU. Oh yeah, here. See. So now we will run each instruction. And this is a fun part because you can do this run instruction. It will receive mutable memory. Okay, wait. And also, of course, self mutable. Okay. What is this anonymous parameters? Oh, sorry. Yeah, so now we have the memory. And we can do this, like let's do this, println. This is nice. This is nice. So we can like copy it from here, and then we will be doing this memory read byte self PC, the program counter, right? It's a 16-bit. So then we can do this PC equals minus 2. Minus equals 2. Oh, sorry, self PC. And it's not returning it. So this way I will read the byte over this address, and I will do this to the end. Still gonna fail, I think so, because it's out of bounds here. Let's see. Nope, didn't work. Didn't work. Why? Okay, actually, it should be. mind. Yeah. Oh yeah, because so let's do something here just because it's well, we have only the beginning of the file, so we have no time to see it there. Is there a print without a new line of code? So let's see if there's a print. Is there a print? I can do this like if self pc less than the okay, just to see this happening. Okay, so we have this. Actually, it should be less than or equals. Oh yeah, because otherwise it will not print the last. So now it will print. No? What happened here? What the hell? So third one, FF. Oh, it's jumping one. Ah, of course. Yeah. Sorry. Do the right stuff. Oh, I don't want this. Yes. Yeah, this is good music. So yeah, so here it is. we can run. So we are reading this each reading in this case, right? Each instruction increment the program counter by one, just one, and doing, because this is here is something that is now related to the length, independent of the size of the instruction. So we will need to check. So for example, the first opcode. Okay, so now we start decoding opcodes. So now we have let me just be clear here. We are reading the ROM from file. I can put it as a ROM. It's a boot ROM for a while, but then it will be a ROM file in the future. I'm reading it, then I'm going I'm inserting the ROM file into the memory, which is an array, a big array of 64 kilobytes. So from 000 to FFF here, and after I put it in the memory, I instantiate my CPU, which will be responsible for processing that ROM. It is running the instruction. Okay, it has received the memory. Of course, this is a very primitive thing because we need to handle display, keyboard, and all other stuff, sound, and everything else. But basically, now I'm able to read from the memory, increment this little nice program counter. So this program counter, which is the pointer that will be saying to me which instruction I'm reading. So then now I can start decoding the instruction. So here this is something, just because the file is okay. So it will be okay. I think if it run it now, it goes to the end of the file and it will panic. End of the final end of the memory, which is FFF. Okay, great, it works. So this is just debugging. So okay, now I need to check how to read. So let's start. The very first. So how can I do that? Okay, I will not increment this. I will do this, and yeah, will not loop. Oh, I can do this actually. The size of file. No, I can't do that because, of course, no, I can't. So it should be a loop, and okay, I will do this, and if you do this, it will. Okay, third one. So this third one is starting of opcode. So this manual has all opcodes. So let's search for 031. No, third one. Any luck? Yeah, third one. So opcode third one. It's a load SP and N, which is load SP and N. Oh, here, of course. Third one. Ta-da! Now I know how to read this thing. See? This is the instruction set. So we have the instruction 31, 31. The size is 3. So yeah, nice. Oh, okay. Let's start doing this. So for doing this, I will do this like yeah, I can create an instruction set actually. Pub structure, pub and no instruction set. So then I can match this stuff and use pattern matching. Yeah, like this. Nice now. Yeah, pretty nice. But how? How I will decode? So if I have something like this, yeah, we attach data to each variant. Great, of course. So we will have this. Okay, so our first variant will be LDSP. With anyway, it is just weird because okay, let's say that's LD. Okay. But how I will. Okay. I think that very basic Game Boy Rust Talk. This one. So here. Sorry, I will. Yeah. Well, so it's too early to do this, I think so. So yeah, I will match directly the byte. So let's do this. Let's do this match. So I will do this. Match main self main read byte self PC. Okay, in if it is 031. Actually, so here is I will read. If I don't record, as I'm doing a match, it in Rust it's exhaustive, so I need to match everything. This is a special one that match anything. So if it's anything besides the ones that I will decode here, it will be an unrecognized instruction. Okay. And which instruction? Oh, this is great. So I don't need this anymore. Why I don't need this anymore? Because so let's do this. Let instruction equals to this. Now instruction. So unrecognized instruction. Okay. Now instruction. Sorry. Actually, strings in Rust is double quoted. So unrecognized instruction. Which instruction? On this program counter. Okay, and we can increment it. Well, we will not doing this here actually, because depending on the size of each instruction, it will increment it here. So I don't need this anymore because now it will fail here because it's not there. So let's see if it works. Yeah, unrecognized instruction. Oh, of course. To put it here. So instruction self. You see. Okay, so the very first instruction is not recognized, but then we will start the coding. If the instruction is 031, let's do something here really like 031. Our first instruction, just to be if it will match. Yeah. So it matches. Now we can do stuff here. So here, so this is LD SP D16. So guys, we are officially starting decoding the instruction set, implementing the opcodes. This is very nice because now we are able to see the things moving around the memory, around the other stuff. This will be nice. So then let's okay. So for decoding this instruction, so let's go to one of these documents that will say to me how to decode. I think it is this one. Yeah. So yeah, here's a nice thing because this is a LD and N and N. What is this? It's used with BCD, so we are using this one. Put value in NN into N. Oh, okay, sorry, I was missing. SP is our stack. Great. So our very first instruction, so let me put value and put D16 into SP stack. Okay, so this probably, if this is an NN, yeah, this is the 16 immediate value, so this is why this instruction will be, so this will be something like this. Okay, I think I can do this. I can then, okay, I can also do something here. I want to see the states of my registers. Implement, because I think format debug, yeah. Oh, I can't, I don't need to do this, I think so. Hopefully. CPU state, it is self. Let's see. Yeah, now we can see this. Great. So we can do this now. We can go ahead and implement, put this. So yeah, how we do this? Well, oh yeah, so actually, how can I do match with multiple files? First match with multi. Here. Great. So here we have one thing that is nice, because we can pattern matching this, all this type of, so we do this as generic, like this. Let's copy this. Okay. So if it is this, or actually if it is 01 or 0 or 0 21 or 0 31, it is a Okay. Okay, so this, and here again we do another match. Okay, I think we can do this, and then match LD again. Let's see if this will work. Match instruction. Okay, so match instruction. Now I see. Can do this then. So let me see. Now DD. LD HL. Is this? Okay. Okay. Oh, I can't. Actually, can't. It should be this. Is this? This is correct. Okay, so it should be LD, 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 LD. So if it's LD, if LD, no, okay, if now LD is 31, then we will still panic just to see if it happens. So okay, this is an LD 031. Oops. Okay. Now let's do this. Oh, sorry. So we process the So this will be so since we know this, so let me do this println. This is LD 031 with image G8 value equals 2 mem read byte self PC plus 1. Okay, so as it is a 16 bit, I need to read 2 bytes. And then after it, I put self PC equals 2 plus equal to 3. So yeah, my self PC is in 0. I read it. It is the instruction. Then I get the next 2, so the size of the operation will be 3 bytes. 1 is the operation, is of the opcode, and 2 are the immediate value. So then let's see if this will work. No. Spectral token. What's that? Unexpected. Oh yeah, sure. Here. This is LD. Okay, so we read this and get this FE FF FE FF, and the next instruction is AF. Let me see if you need to get those values in the reverse way. But it seems that yeah, if you see here, this is the same. We are reading this boot room, right? So it's in here. I think this is that big Indian stuff. Big Indian. How can I say that? Big Indian. Something like this. So let me do this. Oops. Big. Okay. So here our big Indian, as I saw this. The sign date is formatted to complement of those. Okay, so these are okay. It could be have a prefix or an opcode and immediate. See. This is the CB prefix. Now I got it. So okay, the 60-bit images are in big endian. Okay, so we need to reverse. Okay, for just for sake of here, I will just reverse this 2 1. Okay, so then we are this with immediate FFFE. Okay, and then we go back. So I can now I need to actually write this. Okay, so let immediate, let's put this base 60 bit. How they put this at here? Okay, D16 equals, so the immediate 60 bit in big endian. In big endian, that's the how it calls, not big endian, big endian. Yeah. So how this works? It will be like how I will concatenate that into. Okay. Think that is something I need to do bitwise stuff. So let me do this. So let n, so it's and here it calls n. So n is this, but I will read it as a U16, which will be something like 0. Let me see how this works. Okay, so let's do this, and let's do N1 and N2. Okay. And I will, instead of so this is 1N, 1, 2, and we will put 1 and 1, 2. Okay. Okay. Actually, it's okay. N1 and 1, 2. But for reading that, reverting position because it is big endian. So then I do this 16. So it will be a U16 because it's a it should be a bitwise. So I need to get those. So you do this and 2. Just if this will work. Okay, F E F F. So this is like we get this as 16 bit. So let me do this to debug what I just did. So if I do print out and if I do this, see the FF goes from here to here. Then what we do an R with this, and the FL come here because it's 0 0 0 0 0 without. Yeah. Welcome to Bitwise. Bitwise operation. Okay, now that's easy. So self sp. So the instruction says put the value into n. So sp self sp equals d60. Yeah. So we are actually putting this address to the stack. Stack is the way where it will handle how to get back and forth. Okay, so I have this. I want to see one thing in this talk because there was a very good part of this talk where it says what this bootloader does. Says that in each run. Okay.
the chime, and then it gets interesting. It compares the logo, because the game has to have a copy of that Nintendo logo inside. If it doesn't match, the game does not boot. This was meant so that Nintendo could control which games are released for the platform, because all games had to contain the logo, which is not just a copyright violation, but also a trademark violation if you include that and you don't have Nintendo's permission. After that, it also checksums the header just to make sure that you don't have to blow into the pins. And
here, I will pause this. So we are reading this. So at this part is initiating the run. Okay. So we are just putting the SP here and then incrementing. Okay, and let's go to the next step. Okay. So this is the bug. This. Okay, so let me see. Yeah. We have SP here. Okay. So now we need to decode this other AF. Let's see what AF does. AF. Just filling up this will be fun too. Parameters. Yeah. Oh, sorry. It's faster to just go here. A. F. AF. It's a short 8. Okay. Short N, logical exclusive OR, N with a register A results in A. Okay. So we do a short. In this case, AF is a short A. So A with A, it's like keep A as A. Char 0. Char is char 0 0. Char. I'm shame. Yeah, sure. So char operator rust is to be char. What is the operator? This. Okay. Char is true, true, false. Oh, char is the difference. Yeah. Sorry about that. So as we already initialized our A with 0, it will be 0 with 0. It will continue 0 because it will be equals. So actually it's putting 0 right there. It's just putting 0 there. But let's implement this stuff. So now So let me do this. I think all those 8. Oh yeah. So we have this short n right here. Short n is all those stuff. E. Oh, this is nice. AF. Okay. So AF. So let's do this. Now I have another. This is something different. Yeah, because remember that in other we said this special register here. It's does something. It does this. Just the flags. It's a flag. Okay. So if you see, there is no opcode for short in F, because when you do the accumulator, it needs to change the F. So every time we do something in A, we need to update the register F. And this is something else that we are doing now. Oh, it's fun. Oh, so I think it's already almost 2 hours. Yeah, I think this is good. I will not implement AF yet, but I will put it here. I will put this as a. So here. Okay. So, come. What's happening here? Copy. Okay. Great. So it's to do AF, which is the next. Okay. So we can call this a day. We have we have read the ROM file, created our CPU, our memory structure. So we read the file, we put the ROM file into the memory, in the right addresses. Then we create a CPU, and now we are read the instructions for doing that. So we read the instruction, we match the instruction. So if it's one of those values which we got from this document with this dependox, with this like a document that this guy did with the instructions. So with these instructions, right? So as we are reading the file, we got our very first opcode. What it was 31, 031. We get from here 031. Oh, actually from here 0. So third one is an LD SP D16. We can go here to more details. LD SP. LD is just put a value into register. The LD in this case, as is the opcode is third one. Sorry. Yeah, it's not here. This is where. Hmm? Oh no, it's not this one. I think it's actually LDSP. Let's see, LDSP. Oh yeah, actually, wow, it's a 16-bit load, so it's a LDSP and N. Okay, so opcode pin 31, opcode 31, LDSP 16-bit loads. So 1 byte is the opcode, and other 2 bytes are the value that will load into the register, which is SP. So I get the value here. Oh, and there is this stuff. I get the opcode, then I got those two next bytes. S byte in Game Boy, the 16 immediate bytes are in Big Indian. We need to do this stuff. Here I transform this N2. I just move the bits from 8 bits there and put in the first 8 bits, and then I make a OR with the other, so it is now it reverse those 2 bits, those 2 bytes. Okay, and then this is the D16, which is a 16. I put that in LSP, and I increment the program counter by 3 because 1 is the opcode and 2 bytes after that, so we are 3 bytes ahead. Then as we are doing a loop here, it will run this instruction, it will match here. Okay, then I will increment, it will run again. When it is run again, it's not this anymore, it will not pattern matching here, it will not pattern match here, but it will panic with saying to us our state, and it's here. It panicked and instruction not recognized the AF, which is this. Okay, so now we have our CPU state, which have the SP with the value that was FE, FF, FE, so in the reverse way here. So great, we did it. I mean, the very first instruction. Great, that put me happy. Okay, so implemented memory CPU like primary. When I say that, primary, elementary, memory, and CPU, and also the first structure. Great. Push. Okay. Okay. So guys, so folks, I think we can call this a day. Yeah. I'm very happy with this implemented one instruction. Okay. Of course, there's a long way ahead, but that's it. So thank you for watching. See you tomorrow. Tomorrow's Friday, yeah, tomorrow. Okay. Bye. This video will be in my YouTube.